Question 12. An unstable nucleus, not told what it is, can decay by emitting a beta minus particle. Part 1. Which part of the atom is the same as a beta minus particle? Well, a beta minus particle is a high energy electron, so it's not really the same because it has a high energy, but I guess it's the same particle. Part 2. State the changes, if any, in A and Z when X decays. So if this is going to go via beta minus decay, so it's going to go to something else, then the bottom number here is going to increase by 1 and the top number is going to remain the same. It's going to change the element. That's because a neutron has turned into a proton, so the total number of neutrons and protons remains the same, but we've got an extra neutron and we've lost a proton. So the change in A, first of all, well, there's no change. The total number of nucleons in beta decay is the same. The change in Z, that's going to be moving up by 1. Right, part B. Given an equation for this decay. So we'll start off with some element, X, don't know what it is. So that's going to have the same mass number, but it's going to have 1 extra proton. That of course means that the element's going to change, so we're going to put Y. You can put any letter in there as long as it's different to X. If we change the proton number, then we change the element. And to conserve charge, we're going to have a beta particle. You can use a little e there if you want, which is great, but that's going to violate lepton number conservation. So we must have something with a lepton number of -1, which will be an antineutrino. Antineutrinos don't have any charge, so that equation is now observed. It is correct. Right, give myself, actually no, I'll do it here still. State and explain what conservation law may be used to show that it is an antineutrino rather than a neutrino that is released. So let's go back to this other equation. Let's look at the lepton numbers down here. There's no leptons in this first bit, so the lepton number is going to be 0. There's no leptons in this one, it's just the nucleus, again that's going to be 0. This is an electron that has a lepton number of +1, and this therefore must have an electron number, or sorry, a lepton number of -1, otherwise it wouldn't work. Because basically we've got 0 on this side and we must have 0 on this side. So what we're going to write down, well, lepton number is always conserved. And before it's equaled 0, and after, as long as we're using an antineutrino, it's going to be 0 + 1 - 1. If we use a regular neutrino, that will be a +1, and that will mean we have 2 leptons on the right hand side, which is obviously incorrect. Right. Final part. One of these How Science Works questions. They're a bit annoying, but need to be done. What must be done to validate the predictions of an unconfirmed scientific theory? Basically, you've got to test a hypothesis. So the hypothesis is tested by experiment, and then you can either reject it or you can confirm it. But just doing it once is not enough, so it must be repeated or reproducible. You must be able to show that you can do this again and again, otherwise you reject your hypothesis. And that's everything.